This is a makeup recording for day 3 of Cyber Virtual Circuit Lab Advanced. On day 2, we covered capacitors, RC filters, and the basic ideas of signals. And so we're going to start off with some review of that. So firstly, we established that a signal is anything that contains information over time. So whether it's a constant voltage, you turn on a battery and then turn it off, 5 volts or 0 volts, or a changing voltage. For example, what my microphone is transducing from the audio that I'm speaking to it right now. Those are all signals. And what we thought about was that fast signals have high frequency and slow signals have low frequency. Frequency meaning how fast the signal changes over time. So if it's oscillating back and forth really fast, that's high frequency. If it's changing really slow, that's low frequency. And we found that we can represent any signal as a sum of only simple signals, of signals that have a well-defined frequency. So while some signals might look really complex, like this signal on the left here, we can decompose that signal on the left to look like the sum of simple signals like what we have on the right. And this is just a demo of that. So if I reset this and I just draw some strange shape of a signal, if I asked you what the frequency of that signal is, you couldn't tell me. But I can represent it as the sum of terms that all have very well-defined frequencies. And as I add in more and more terms, we get closer and closer to the actual signal that we're interested in until we eventually perfectly approximate it. So that's sort of the point of this analysis. By analyzing circuits for their behavior frequency by frequency, we can understand their behavior to any arbitrary signal. We also discussed why we might want an equalizer circuit. You might be interested in turning up the bass in your music or turning up the treble in your music. And this is a way to do that with hardware. We then discussed capacitors and the fact that capacitor builds up charge over time on its place due to the voltage from a battery. And that buildup of charge is what causes a voltage difference. Remember that a positive charge sitting up here is going to be pushed away from the other positive charges and attracted towards the negative charges. That's an electric field. And so that electric field and the movement along that electric field is a potential difference. We have a voltage difference across these two plates. And because charge can't teleport, the voltage cannot change instantly. And that's the defining property of a capacitor, the fact that voltage cannot change instantly on a capacitor. And as a result of this, we see that capacitors act as low-pass filters. So let's first look at the DC. If I turn on the capacitor, you see it takes some time to react. If I turn it off, it takes some time to react to that as well. But if I turn down the capacitance, if I decrease that time constant R times C, now the capacitor reacts a lot faster. If I go to the AC simulation, we see the same thing. Notice how high the capacitor is getting in response to the high frequency wave, okay? The battery's going up here, the orange line. The capacitor is getting maybe up here, okay? If I decrease the frequency, notice that the battery amplitude, how high the battery voltage is getting, it stays at the same point. But now the capacitor voltage is able to reach where the battery gets up to. The capacitor can react fast enough. So a capacitor, this voltage, if I have a circuit where I'm measuring with my voltmeter the voltage across the capacitor, this will act as a low-pass filter. At low frequencies, I will measure the full voltage. At high frequencies, I'll measure nothing. And you can modify this logic to get a high-pass filter. If you measure the resistor instead, you'll have a high-pass behavior. So in this lesson, we want to solidify some of the terms that we talked about last time and just get clear on everything. So firstly, what is gain? Gain is going to be what I just drew here, that ratio of how high the capacitor gets relative to the battery. The amount of voltage that gets through from output over input is equal to gain. That's by definition. And typically in circuits, this gain can be like 10 to the 8th power. It can be massive. And so it's convenient to express it on a logarithmic scale. And that's what we're doing here. So on the left, the gain is 10 volts is the output and 1 volt is the input. So the gain is 10 in terms of just a ratio. But because we want to express that in decibels, we would say the gain in decibels is 20 times log, by the way, base 10 log, I should say, log base 10 of 10. And that's just going to be equal to 20 decibels. Okay? So 20 decibels is the gain of this thing on the left. The reason that it's 20 is because really it's going to be proportional to voltage squared. We like to talk about power gain, not voltage gain, and power is proportional to the square of voltage when we think about resistors. So as a couple of other examples, if the circuit took 1 volt to 100 volts, what would the gain be? Same for these other two. You can take a second and work through that. The answer to those being 100 divided by 1 is 100. Log of 100 is 2. 2 times 20 is 40 decibels. For the second example, 0.1 divided by 1 is 0.1. Log of that is -1, so negative 20 decibels. And the most important one, no change, is 1 volt to 1 volt. That's log of 1, which is 0. 0 times 20 is 0. So if my circuit does nothing, then the gain is 0 decibels. That's another reason why decibels is a convenient scale. The do nothing point is at 0, which is nice. It's a nice feature of this scale. Some other terminology that we like to use is the cutoff frequency. So the cutoff frequency is defined as where the gain decreases by 3 decibels from the passband. So what that's saying is if I make a plot of gain over frequency, the cutoff frequency is going to be where the gain has decreased by 3 decibels. So if my gain over frequency looks like that, maybe that's 10 decibels, but then as we go to higher frequency, it kind of peters off. Wherever 7 decibels is, maybe it's right there, maybe that's 7. That's going to be your cutoff frequency. Okay. And we typically annotate that with we typically annotate the cutoff frequency with F sub C or omega sub C, which is the angular frequency. And again, this is typically the shape you see for these curves. Notice here at low frequencies, the capacitor is tracking. If I increase the frequency a bit, the capacitor still tracks. But if I increase the frequency more, you can see the capacitor gets quite bad at tracking the battery, and even worse and worse at high frequencies, right? At very high frequencies, it can't do anything. So yeah, the cutoff frequency is where the gain has decreased by 3 decibels. This is not specific to low pass filters. It can apply to high pass filters, which would look something like this. Then your cutoff frequency would be around there. Or even band pass filters, which we'll talk about in a second, where you might have this. Then you just have 2 cutoff frequencies, a low and a high. So if my initial ratio is V out over V in, and we'll call that A, what percentage of A does it mean to decrease by 3 decibels? This is just a math problem that you can work through. It turns out it's about 0.707 or 1 over square root of 2. So I encourage you to work through that yourself. It's just algebra and math, but that's an important number to keep in the back of your mind as you look at these circuits. Now, bandpass filters is what we just discussed. There's going to be 2 cutoff frequencies, but as I just said, the definition is the same. It's where the gain has decreased by 3 decibels, and that's gonna be the same thing no matter what. Now, notice how the frequency here depends on 2 pi. You might also see omega equals 1 over RC. Because everything works with sines and cosines, it turns out pi is quite important as a letter when we work with these circuits. And so if you see factors of 2 pi, it just comes out of the fact that sines and cosines are things that dictate everything. And I won't get deeper into that, or you could just take it at face value that it's a math thing. But this is the formula that gives you the cutoff frequency for a simple RC filter. And notice if I increase the reaction speed, or sorry, if I increase the time the circuit takes to react, so RC goes from 5 seconds to 1,000 seconds, we have a very slow circuit, then the cutoff frequency gets very low. So a slow circuit has a curve that looks something like this, whereas a fast circuit has a curve that looks something like this. Okay, that's going to be what the frequency response curves look like for an RC filter. Some other important words are the order of a filter. So here you can see we have a filter that goes from 1 volt down to 0 volts, right? So it's not giving any gain. It's just a filter with no gain with a 1 volt input. And sorry, V out over V in is I was understood. Let me rephrase. We're plotting V out over V in. So the y-axis here is just the ratio, not in decibels. Okay. And so notice this point right here is about 0.7. That's going to be our -3 decibel point. So right here is the cutoff frequency for all of these filters, exactly at this point. The low order filters, for example, n equals 1, has a small slope, or rather a very flat slope. Whereas the high order filters, like n equals 8, have a very steep slope. So depending on what your application is, maybe you really need 0.9 hertz to be passed through, but you can't have anything of 1.1 hertz passed through. Maybe you have someone with a really sensitive ear who can't tolerate that high frequency in their ear. Then you need a really steep filter, and that comes with difficulties in building that filter. You need more components generally to do that. Whereas for a low order filter, you need less components, but you sacrifice a flatter curve where you're letting less through in the pass band and you're passing more through in the stop band. Stop band is what we call the stuff that does not get passed. Now, we also talked about bandpass filter terminology. So the quality factor generally refers to how wide the filter is between its low and high cutoff frequencies relative to what the center frequency is. So here the center frequency is about 1.6 kilohertz. And this filter, the green one, has a very large bandwidth, is what we call it. There's a very wide range of frequencies that pass through. And so because there's a large bandwidth, we generally say that the quality factor is poor, Q equals 1. Whereas this the yellow circuit in the middle here, it's rather narrow. The bandwidth is tiny at the same cutoff frequency, or same center frequency. So this one has a much higher quality factor. The reason quality factor and bandwidth are important terms, quality factor in particular, is because the math of dealing with circuits that look like bandpass filters is very general. It's just the theory of second order differential equations. We won't go into that math, but the terminology comes out of other analysis that we tend to do in that math. And it's interesting to think about, for example, lasers. So if I go to I'll just write it. So for the average laser, maybe a green laser, I think it's going to be like 5 times 10 to the 14th hertz is the center frequency, okay? So I think that's about the frequency of either red or green light. I forget which wavelength, but it's within the visible spectrum. So say you have a laser that has a 100 nanometer, a 100 nanometer bandwidth of frequencies that it's letting through. 100 nanometers above or below green light is from 432 nanometers to about 632 nanometers. And if you do the math, that ends up meaning that the quality factor of the laser is massive. It's orders of magnitude higher than this Q equals 100. I think 10 to the 8, I'm just guessing, but I think 10 to the 8 or even larger than that is like rather standard for a laser. And so I'm just guessing that I might be wrong about that, but it's very large. And so this quality factor is very important for also comparing different systems that we use the same mathematical theory for. So that's the last thing for day 3, relatively just a vocab lesson basically. And yeah, that's that.